Okay, so just to start at the beginning, so what I'm going to do is I'm going to do a bit of a chronological approach to describing the work. Hopefully that'll also be kind of logical at the same time. So the conception of the project is basically, the premise here is that vocal exploration or babbling is a critical process during early vocal learning and speech acquisition in general. And one of the early experiments prior to this project made the observation that if you combine an articulatory synthesizer with some critical assumptions, phonetic assumptions that reduce the articulatory degrees of freedom, and you have auditory feedback in some kind of simulation, it's possible to discover intelligible syllables even with an algorithm like random exploration. So this is really kind of the seed for this project. And then basically the questions going forward from there are, so what are the critical mechanisms that support implementing a working simulation of vocal exploration, in terms of articulatory phonetic aspects, sensory, cognitive, and algorithms or processes needed to actually make progress on this task. So emphasis here also on the working simulation, because basically one of the objectives of this project is to have some sort of quantitative evaluation of the outcome. So this is related to intelligibility of the outputs. We'll see later. So let's begin with discussing babbling. So we'll start with more kind of observational studies. So how do we start with simulating babbling or vocal exploration? Okay, so firstly, we can refer to what's already known about this in actual infants, and what's already been characterized can be broadly described into four kind of stages. So from early stage, where infants basically just experiment with voicing and resonating sounds, the so-called phonation stage, into gooing, where you kind of get vowel-like sounds and uncoordinated kind of obstruents and syllable-like sounds, to the expansion stage, where you really see exploration and exploration of different kinds of sounds, manners of articulation, things like that. And then the so-called canonical babbling stage, which is associated at the final stages with kind of well-formed CV syllables that are kind of reduplicated, and the sense is that this is basically the basis for kind of a phonological unit that you can use in speech production. So those are in terms of the observational side. And then, of course, if we go look a little bit further, more broadly in terms of speech acquisition in general, we can also see that you can kind of look at the perceptual development side of infants. And these things happen kind of in parallel. In the literature describing perceptual development, usually the stages described there are one of universal perception, which is at that point not really biased by the language context. That moves on to firstly language-specific perception of vowels, and from there perception of sound combinations, leading to kind of typical first words around 12 months. So one thing to take into account when we're implementing vocal exploration, which is what we have here in babbling on the left, is also what is happening during perceptual development. Okay, so how do we take this picture to, let's say, computational implementation? So what we have tried to do is take these stages, have some kind of broad interpretation of what are the mechanisms, the outcomes, the inputs and outputs of these stages. And so we have to kind of contextualize what our computational simulation is going to be about, have some kind of hypothesis about what is happening during these stages. So we're trying to implement the actual mechanisms here. And so the picture we have here is that you could broadly associate these kinds of stages with different, let's say, abilities that the infant is acquiring during those periods, from laryngeal control to coordination with the upper vocal tract, basic sensory motor control, being able to control the articulators in a stable sense, and then leading to language-oriented sensory motor control. So basically learning how to produce phonological units, and keeping in mind that language-oriented perception develops in parallel as well. So those are potentially some of the inputs to this process as well. Okay, so and then finally, this slide is trying to contextualize what we're essentially focusing on and some of our assumptions. So we start with a number of phonetic and kind of cognitive assumptions. For instance, synchronization of control of the larynx and upper vocal tract. We start with a mathematical model of producing articulatory trajectories. So this, to some extent, captures what we assume is learned during basic motor control of the articulators. And we focus essentially in our work here on what is considered, and often considered in a lot of computational studies, as a goal-directed explorations process. So this is a process which is moved away from being kind of a random search to something where you actually have some objectives that you're trying to either imitate or produce. And so this is really the part of the exploration process that we're implementing. Okay, so our first attempt at implementing this basically was an attempt to extend the previous work, and there's a lot of technical and other aspects that we would like to make progress on or extend in our first attempt. Firstly, the previous paper was one with random search, and we would like to have a more efficient process, something based on optimization algorithm, and using auditory and articulatory constraints to make this process more efficient. We experiment with, at this point, we still experiment with acoustic matching as the auditory objective for feedback to do this goal-directed learning. And we recognize that the goal is language specific, and so the goals at each point are essentially template utterances from that language that you're trying to imitate. We test some articulatory phonetic constraints. So one critical one is syllable synchrony. So in these sets of experiments, we test how well the process works with and without this synchronization condition, which to some extent is motivated by observations of coarticulation. And lastly, we in the previous studies, we did actual listening tests, which is a good way of quantifying intelligibility. But in this study, we also use something like automatic speech recognition to see if we can actually improve the efficiency of our experimentation process or the methodology. Okay, so basically what we did is we set up these simulation of an optimization process simulating goal-directed exploration, where we had a set of words from which we took CVs. So these words have well-defined meanings or phonological contexts. We did vocal exploration to imitate these CVs, and then we embedded this in words again and presented it either to listeners or to an ASR system to quantify how well what the word recognition rates are for our outcomes. And we have basically three different outcomes here, things that we learned from this experiment or these sorts of experiments. Firstly, yes, it's possible. So on the left here, I have word recognition rates for firstly different algorithms, with random search being one of them. And we find that certain algorithms are better at this exploration process in terms of the outcomes. The other thing that's tested here is the kind of correspondence between word error rate for our listeners and for the ASR systems. And we see that, again, the kind of word recognition rates are actually comparable between listeners and the ASR system. Listeners are typically slightly better at recognizing the words, but they are basically in the same on the same level. And if you delve into the detail, you see kind of similar patterns for the particular words as well. And then lastly, as I said, we tested different assumptions of synchronization. And we did this by essentially tying articulators between the vowel and the consonant for the vowel and consonant segments and seeing what the success rates are. In some cases, especially for bilabials, this significantly increased our success rates during the exploration process. In other cases, it was more or less the same, whether it was free or synchronized. And in some cases, we actually got better results with a free setup. So that kind of, to some extent, gives you. In this case, the tying we've done are basically manually defined, and so it's not always possible to select an optimal parameter tying, from theory. So those are the results we got in this set of experiments. So what were the limitations of this approach? So we basically learned a few technical. We made some technical progress in the study, but we also need to recognize some significant limitations. So firstly, the auditory objective function, acoustic imitation in this case, was not possible when there's a speaker mismatch condition. So we were able to do, so the results you see in the previous slide are when the vocal tract, which is based on a male speaker, imitates speech by a male speaker. Once we change that condition to try and imitate speech by a female speaker, using acoustic matching, the recognition rates go down, but the process is less successful. So basically, we have this is well known already, the so-called speaker normalization process, and it basically indicates an inadequate goal space for this problem. Secondly, imitating single utterances again is not well aligned with the evaluation function. In this case, we're expecting a good word recognition. And there's no guarantee that a single utterance is going to be a good template to reproduce to maximize word recognition. So we also have the problem of in this, we can call this the phonological correspondence problem. So this is also a well-known problem, and this to some extent indicates an inadequate essentially goal that we're trying to achieve, that's defined in that space. Another limitation of those sets of experiments are these tied articulatory parameters. So to some extent, by choosing from theoretical, using theoretical knowledge, which parameters to tie up, we are injecting some kind of phonological knowledge into the simulation, which we're not really interested in doing. So what we want to do is define these constraints or objectives in more abstract terms, and then actually discover the coordination of articulation during the process. So, of course, these are a number of significant conceptual problems. So there are a number of ways that these kinds of problems can be solved. So how do we proceed in terms of technically solving some of these problems? So if you look at speech technology, some of these problems are solved, for instance, on speech recognition by vocal tract length normalization for speech recognition systems. If we want to learn from more than one template sound, can we define normalized acoustic templates over multiple speakers? What should we be doing in terms of improving the goal and the goal space for these simulations? So instead of just implementing this, we can take a step back and firstly define, at least for our purposes, what we mean by speech acquisition or computational speech acquisition. So I give here basically a kind of definition of speech acquisition, to some extent a bit narrowly defined around what our aims for the project, but basically the definition is as follows. So we have an agent. We want this agent to acquire the ability to both perceive and produce an utterance with a specific phonological function by using articulation similar to what a human can be. So an illustration of this definition is on the right here. So basically, you could see if you could implement something like this, where you have a sound, a phonological utterance representing a phonological unit as an input, you can perceive that sound firstly, and then secondly, reproduce it with your own articulators to produce the same kind of equivalent phonological utterance. then we define that as this agent has acquired has done computational speech acquisition. So what does this involve? So now I'll go in a little bit in terms of details of how we kind of break this down. So it involves on this perceptual side auditory processing model and an auditory perception model. So the basic auditory processing model we assume is a kind of physical process, so that's not a learned process. So the blue blocks in this illustration are essentially physical processes that you can model directly by a mathematical process, and the red blocks here are assumed to be learned mappings for processes, right? So firstly, auditory perception is something that's learned. Then you have some way to reverse the process to basically predict what the articulation should be given a phonological unit. And then you have some way to actually turn that into a motor trajectories that actually produce the speech. So those are all assumed to be learned. In our framework, we take this last block as a given as well in terms of a mathematical model, so we don't learn that. And so what we're interested in is learning these two blocks, so the perception and production models. Okay. The implications of this kind of view on speech acquisition and how it could be implemented computationally are that the perceptual model is to some extent dependent on a phonological representation, which is connected to the perceptual model. So there is some dependence there between the production articulation model and perceptual model. And basically, we assume that the process that we're trying to implement essentially the products of that process are, like I said, this acoustic to perceptual mapping, perceptual to articulation mapping, basically an inverse model, and likely also a model that actually allows you to do forward mapping, so to predict your own the outcomes of your own articulation. So that's taken a step back, defining computational speech acquisition, at least in the narrow terms for the purposes of our project. So let's look again. So how can we attempt to improve upon our previous simulation? So don't worry too much about the grayed out part. So essentially what that means is we keep the same idea as our first implementation. We still see this as an optimization process with auditory and articulatory objectives. We now try and improve upon our auditory and articulatory objectives. In the auditory side, the question is really, can we construct a more appropriate goal space based on some kind of grounded language-oriented perception? And how can we define, let's say, phonological goals in this space to drive the exploration process? The second part is essentially trying to get rid of manually tying parameters. So we're interested in separating articulatory objectives because we have quite an abstract optimization process. We separate our objectives conceptually into what can be seen as some of the sensory targets for the agent. So the agent can sense, let's say, closure or an opening of the oral tract. And so those are kind of conscious targets that the agent has learned at some point prior. And regularization objectives could be learned prior behavior of lower level abilities, articulatory control, or physiological or cognitive constraints. So, for instance, the fact that it's not possible to coordinate, too many degrees of freedom in terms of articulation. So you assume some regularization process happening there. And we are also interested in just reusing our methodology of the ASR system and listeners. Okay, so how can we construct such a phonological goal space in a kind of data-driven way or in a computational way based on some process? So we take, again, please don't try and read all of the grayed out sections. That's just really placeholders to show some publications. But basically, there are three. We take some prior work in from three different areas. So firstly, there are existing computational vocal exploration studies out there, and some of them try to create such a phonological goal space in the process of vocal exploration. So they typically use self-organization of self-generated utterances. So as the agent does vocal exploration, you learn some perceptual function of the speech that gets generated, or there is some process of feedback where a teacher actually provides corrective action or some input that allows a phonological goal space to be constructed. So this is a algorithmic or data-driven way to construct these goal spaces. Secondly, from the more perceptual, computational perceptual studies, where they don't consider articulatory learning or vocal exploration, there are indications that it's possible to use distributional or self-supervised learning to construct such a goal space from either from the acoustic data alone or with some semantic context, whether it's, to what degree the semantic context is necessary is not clear, but the combination of semantic context and acoustic data or acoustic data alone, you can already make some progress in terms of construct such a phonological space. And then in the last study, or the last paper, there is essentially a proposal that one of the best ways of doing this is to create a rich multimodal environment where you actually have semantic context, you have other contextual information, you have speech data, and then try and find out how to combine all of this to create a phonological space from which the learner can learn. Okay, so some comments on some of those aspects. So in the first case, the main advantage is that those computational studies account for both perception and production and how they can co-develop. The downsides are, in a lot of those studies, essentially perceptual development is tied to the onset of babbling or vocal exploration. So there can be no real, in those accounts, there's no real perceptual development prior to babbling or vocal exploration. In a lot of the studies, there's a limited stimulus from which to learn this perceptual or phonological space. It's either self-generated utterances or utterances by one or two caregivers, and so there's potentially a need to actually include more stimuli in that process. Some of the advantages seen or findings seen in the self-supervised learning studies are that this perceptual development is possible on the basis of acoustic and semantic data alone. And in the last study, one of the main downsides are essentially that you have to construct a rich data set, which is really difficult to do to incorporate potentially all of the necessary information and context you need to proceed with vocal exploration. So how does that lead to our approach? So this takes a little bit of a pragmatic approach, but so we define a kind of computational developmental model here, which involves learning of a perceptual model, which provides a phonological space. We define a process of articulatory exploration, which is what we've been implementing up to now. And then we essentially assume that there is some dependence on between these processes. So, for instance, this auditory perception model, which is the output of this process, which could be bootstrapped by a caregiver with distributional self-supervised learning, that's uncertain. Essentially, this model is required in the next part, at least to partially exist, for articulatory exploration to proceed. This generates self-generated data, which is what the agent will need to actually learn articulatory models. So there's some kind of dependence, even though the assumption is that these do develop in parallel. There's some basic dependence there that something needs to exist before the next stage. This is our assumption here. So in our second attempt, what is our essential contribution going to be in terms of incorporating such a model. So we look at the process in terms of, let's say, information sources or signals that are available to the agent to learn or do vocal exploration. And this compares what other computational studies have considered, as well as what we're proposing here. And that is that, so essentially we have different data or environments or conditions. We have some processes here. So this is grounded auditory perception, and we have signals that carry this information. So we assume that we want to learn from multiple speakers in a context of a specific language. That's represented in terms of acoustic data. You have some semantic context from the environment. The caregiver is also part of the environment, so the remaining environment also carries some semantic context, and this can be perceived through different senses. And then you have acoustic links from the caregiver, visual links that can drive, can help with development of either the perception or articulatory exploration aspects. So what we would like to include here is grounded language-oriented perception that can influence articulatory exploration. So it can exist prior to the actual process of articulatory exploration. And we want to include the contribution of multiple speakers in ambient language, which hasn't been done before, really. So we look again, so this is essentially our implementation of that. Again, it's similar to our previous attempt. We start with an optimization process, where we have some articulatory sampling of the articulatory space. We try synthesize those trials, and we measure how well we're doing in terms of our objectives. So our objectives are defined in terms of kind of language-specific auditory objectives and speaker-specific articulatory objectives down here. So the main aspect here is that we take a pragmatic approach towards constructing this language-oriented space. So instead of using a rich multimodal data set, we use a speech corpus where we actually have semantic information in terms of transcriptions, and we use that as a proof of concept here. In this case, we use supervised learning, and we construct basically a recurrent model which maps an utterance to a phonological space. So this is a neural network that basically just does a mapping in that sense. And then we can use that to evaluate synthesis by the agent. So if the utterance gets synthesized, we can put that through the syllable encoder, get a representation, and that can be part of the objective function. And on the speaker side, we implement tests against the tube area functions of the articulatory synthesizer to test various aspects like closure of the oral tract and things like that. So, and the outcomes are essentially articulatory targets that represent the exploration towards these goals. Okay. So just an illustration, so the syllable encoder, basically, like I said, it's a recurrent neural network which takes an audio sample as input and then outputs, in our case, the phonological space is defined directly manually through supervised learning. But in principle, that's not really necessary. Basically, the idea is to just define a low-dimensional space which represents some kind of phonological information. So whether that's derived in different ways, in our case, we use supervised learning, the speech recognition corpus to perform this function. So you get something like this. It's slide here.
the
Sorry, Justin, those of us on Zoom can't hear you any longer.
Yeah, so basically I'm just illustrating here, as the speech comes in, you get an evaluation from this perceptual model, which maps this to a fixed vector in some kind of phonological space. In our case, this is predefined in our experiment. Perhaps the next slide is actually just a bit easier to evaluate. Okay, so this is just another static view of that. So there are a number of advantages to this model in addition to the conceptual issues we discussed. The other one is just that it allows us to do kind of contextual dependence in weighting frames. So instead of having kind of a naive frame by frame distance measure, the network can do that in a contextual way. So we see here, this is kind of the evaluation by the recognizer in this phonological space as the speech comes in. You can see it kind of reflects kind of a prior probability, I suppose, based on the data set we trained it on. And as the speech comes in, you can see that the evaluation changes. So initially it's ba, then it changes to a d, initially do. And as you get enough speech, you see it converges to an evaluation of D. So this is basically the perceptual model that we used in the experiment. And what we have is a fixed vectors output. For the articulatory objectives, we use the synthesizer's tube area functions to essentially evaluate a number of articulatory aspects. So we can see whether there's a closure being formed at a particular place in the vocal tract. And we can define a set of loss functions or a vector, if you want, that represents this information. And we can use this as an articulatory objective during the optimization process. So some of that, I'll discuss in the next couple of slides. But basically, this is the combination of two types of losses. And we basically have two experiments that we set up. One to test our two different acoustic or auditory objectives to imitate specific utterances. And we also have one where we test different articulatory objectives using our ideal percepts in this phonological space. And I think I'll just skip forward. So the first test, we tested essentially our old acoustic matching against a comparison in this phonological space. And we can see that the problem persists for acoustic matching, that if you try to imitate a female speaker, the performance in terms of the word recognition rate drops. But this doesn't happen when in our phonological space. So basically this is just validating the ability of this phonological space to represent speech by different speakers and being able to compare that in that phonological space. And then secondly, we tested different sets of articulatory objectives. And we find that objectives that prefer kind of a greater degree of co-articulation actually result in a higher percentage of success. So we more often get higher word recognition rates if we include these kinds of objectives that basically prefer co-articulated solutions. So I'll just show you some comparison. So I don't need sound here, that's fine. If we have a simulation where we don't care about, let's say, co-articulation, we can end up with, this is for de, the CV syllable de. We get solutions like this, where you kind of have the tongue all pressed up against the palate. It sounds fine. Okay, so I probably can't play this. solutions sound the same, but they are drastically different solutions. So here we have the solution where we actually have a coarticulation objective. So there's very little movement other than the necessary movement by the tongue to produce the sound. And to some extent, surprisingly, the latter actually, because if you think about it, our evaluator at the end of the day is just an auditory test, whether a listener or an ASR system. So to some extent, surprising that having an objective other than auditory improves the success rates, but I'll discuss some of that later. But that's one of the findings. Okay, so to come down to the limitations of the study, so we're still working with CVs. We're interested in greater language coverage, more complex syllable, consonant clusters and syllables. But the articulatory solutions, we've not found a good way to quantify this, the solution. So to prefer more prototypical solutions, or at least measure how prototypical the solutions are. There are other aspects that need to vary in a really realistic scenario. So especially duration, which to some extent has a phonological function in a lot of languages, but also prosody and speech rate. And the articulatory models, we still want to actually train articulatory models based on the samples generated during this exploration process. So we haven't trained models yet at this point. So from here, some ongoing work. So in the direction of greater language coverage, we've started working on more complex syllables. So with CCV syllables, we have some sets of experiments where we also test, let's say, sequential optimization. So is it possible to independently optimize the vowel segment, and on that basis find the correct consonants, or do we have to optimize everything jointly? And there are clearly some strategies that work better than others. So if you take something like the syllable clue, it's possible to find a vowel and then the first consonant, so then who on the basis of who, and then the L on the basis of who. That works quite well. But if you just try and add the consonants from the back, that doesn't actually work very well. So who, lu, and then clue doesn't actually succeed very often. So that suggests some dependence on the kind of let's say the solutions possible for the intermediate consonant. That's difficult to do if you do that one first. And then also we've done some work on actually training models. So what would models look like? Articulatory models look like, let's say, an inverse model in this, given this phonological space and the fact that we are learning targets instead of trajectories. Well, basically, we have some auditory articulatory perception. So the concatenation of our auditory perceptual space and the articulatory functions that we specify for certain contexts. And we should be able to map any sound into that space. That becomes essentially the input to an inverse model. That inverse model predicts, let's say in this case, the targets for C and V. And we can then synthesize that and evaluate it again in terms of perception, or we can actually predict what would the perceptual consequences given the CVs that we are intending to produce. And this allows us to do inverse model training. Of course, just directly training inverse model has a lot of technical problems. So I'm probably don't have time to go into that, but essentially you have a non-convex optimization problem there, which doesn't work well with gradient-based learning methods. And so at this point, this is still ongoing work because there are actually a number of choices to make in this training process. So how often do you update the forward model? How do you update the inverse model? There are actually two different error signals that you can use. one which requires synthesis of new samples, the other one which doesn't. So can you use both? Should you be using one or the other in terms of efficiency? There are a lot of kind of technical questions that basically we're still working on. Yes, there's some progress. So if you do this kind of training, you can see that. So let's just look at the blue and orange lines. The orange line is essentially the auditory objective during this training with forward model, and the blue line is the articulatory objective. And we see that it's possible with this kind of gradient-based learning to improve on an initial model that we just trained directly using this process. Yeah, we still need to formally evaluate that in terms of intelligibility and more concrete evaluations. Okay, so lastly, what is the outlook of this work? So basically, we see one of the contributions to what we've done so far is to establish a kind of methodology with a quantitative way of, measuring if we made progress, whether in terms of including a mechanism, an algorithm, a specific goal, a specific way of exploration. So we have a well-defined quantitative kind of methodology. We have a kind of conceptual model here. And now what we can do is we can actually change some of these aspects. So currently, the process is quite abstractly defined in terms of an optimization process, but you can now imagine kind of specializing some of these models or processes to be more realistic. So for instance, instead of using supervised learning, we can actually try some of what has been done already in the perceptual learning space, and then plug this into this kind of exploration algorithm, exploration experiment to see if it has any effect or it still works. We can discover or test phonetic assumptions about articulation. We can continue doing some of that, especially when it comes to more complex syllables. There might be some interesting findings there. And there's still some, on the computational side, questions about how does some of this feedback. So each of these steps can still feed back into the previous step as well. As you're producing speech yourself, this can update your auditory perception model. And the same here, as you are doing gradient-based learning, you are also producing more speech, which you can use. And then the last question on the conceptual side is this enough to synthesize some form of intelligible speech in longer utterances? Or do we need more levels of optimization or refinement? So if we just concatenate these, let's say, phonological units, in this case, syllables, what is that going to sound like? What kind of processes need to be on top of that to actually get to fluent speech, right? On speech technology side, this kind of model that we have here, once it works and produces these models that are that let's say cover a particular language, you could use this phonological interface to in a kind of traditional text-to-speech system as the interface for, let's say, the acoustic model of that. So you can have your NLP components in your text-to-speech system. It needs to produce a phonological specification, and then potentially you can use the articulatory synthesizer to produce the utterances. This might be quite useful in low resource languages. Low resource being either limited amounts of data or expertise to build systems like this in different languages. I'm almost done. So this is some interesting features of our framework, specifically some of the choices we've made. Basically, the articulatory gestures we learned are based on these low dimensional kind of language-oriented perceptual representations. So we are learning, let's say, a motor movement based on a kind of higher level, representation in terms of the function of that, of the outcome of the speech. So this is similar to findings where you observe that there are cognitive representations on the functional level rather than just the low level movement of motor movements. It's in this kind of setup where, again, our articulatory models are based on perceptual representations. It's possible to compare predictions with the articulatory forward model in the perceptual space. So you can kind of start imagining a feedback loop where you actually can use your articulatory models to perhaps add information in terms of an utterance you've heard in different ways to aid. There's some efficiency in the input. It's an interesting observation. So there's been recently a paper which has linked kind of which parts of segments and phonological units are most perceptually relevant. And it happens that in our model based on a target approximation, you will basically have something like that as well, where essentially both your articulatory and perceptual spaces are focused on the endpoint of the segment. So because you're doing target approximation towards a specific target, and everything's based on these targets, that's essentially what you will end up having. An interesting aspect computationally is that because we have chosen the same units of perception and production, you kind of have a context-free mapping between those, which actually might make it a lot easier to train these articulatory models, especially with the forward model, because those models only need to be feed-forward models. They don't need to be recovered. So the only recurrent model in this sense is the perceptual model, and the rest of the models can actually be feed-forward models. So that's interesting from a computational perspective. So open questions. So why do the regularization objectives improve the recognition outcomes? So is it just a case that it finds a kind of subspace, a small subspace where you have more good solutions? So it's a matter of you have a finite amount of exploration, and so you're just more likely to find something in that finite time. Or is there, and this is, I believe, probably the case, are there reasons why these prototypical solutions have some functional advantage in speech perception? And that's very possible, considering that there's a lot more aspects, duration, speech rates that comes into play, which we haven't well tested. So it's possible that we might discover that when we broaden the scope of our experiments, we start understanding why certain solutions are preferable in terms of recognition rates. And then there are a few other questions. So can we replace supervised learning with self-supervised representation learning or something else? And how much semantic context do we actually need? Can we do that based just on acoustic information, or do we actually need semantic information? How much? Those are open questions. Potentially, we can answer some of that by building different models and actually running the simulation. And the last one is the model I gave you with the 3 stages. They basically have different types of processes, different objectives. They're all related, but can they be essentially unified in a reinforcement learning kind of framework? It's unclear whether that's actually possible or not, but potentially that would be interesting to consider. This is kind of more just an advertisement. So some of the tools we've developed are essentially Python packages. So we've created a little kind of Python notebook, which shows you how to use some of this to get some of this running. So if you're interested, this kind of framework I've shown here is implemented, and there is a how-to try it out if you're interested. So to some extent, computational types of studies are potentially more useful in terms of generating good questions rather than answers. So I'm thinking, I feel like that's perhaps what we've done in this project, but yeah, hopefully you find it interesting. Thank you very much.
Thank you very much. I know we have a slightly late start. We still have a bit of time for questions. If anyone wants to ask a question, could take questions on Zoom as well for possibly 5 minutes? Is that yeah, and then we can we'll move we can carry on the conversation elsewhere as well. But yeah, does anyone want to have a question to ask? I think this is interesting. Is it how
I can kick. I mean, I like this idea of the semi-supervised representation instead of the top, you define a phonological representation. And because there are a number of these now which are based around predicting the signal. So effectively you train a system, you have like a spectrogram and you make holes in the spectrogram, and then you try and predict what the content of the holes were. So effectively you try to build a statistical model of what spectrograms look like. And you'd hope that would ultimately learn some phonological representation. So you think that is that sufficient, though, you think, to be able to make something like that and replace the phonological model? Or is there you still need phonology because you still need to know that Paul and ball are different words?
Yeah, I mean, that's a good question. The best way is to test to see how far you can go with that. I believe that you'll certainly improve upon naive ways of doing acoustic matching very easily. I still assume that you need some phonological or semantic context. The question is just how much you need, because I essentially think that it's basically a function of those two types of processes. One, which is analyzing the data distribution itself, but the other one needs to link. That's basically the phonological correspondence problem. You need to link that to something. And this is where this study is way too abstract. The question is, how do you form those links? What is the role of the caregiver in real life? Is it really to give corrective feedback, or is it to clarify the semantic context, or to direct attention? I mean, those roles are potentially highly relevant for that kind of view. Yeah. But I assume there needs to be some.
Does anyone want to follow up on Emma?
Yeah, I had a question. So in the first model that you showed us, you had, I think, a fixed auditory processing node, something like that. And then the next model you showed us that wasn't in there. So I wondered what that auditory processing node did in the first instance, and whether you tested whether it was important, and maybe found that it wasn't.
So in the first model being
sorry, just for the purposes of on Zoom, could someone repeat the question, please, so we can hear it?
Yes.
Sorry, could you repeat the question?
Okay, so the question. So I'm just trying to hear the question. So firstly, here I have an auditory processing component, and then later on I so actually I think that's been perhaps slightly misleading. So you mean this one, for instance? Okay. So actually, this model still contains that auditory processing.
So what is that?
Essentially, it's essentially feature extraction. So in our case, we're just using the same features as in an ASR system. So male frequency capsule coefficients. So this essentially, you're taking audio in. There's a feature extraction, and then the neural network is mapping MFCCs to.
Okay.
Yeah.
It is basically a speech recognizer. In fact, it is the key. It is the key.
Okay, I've got one more question that's coming from Zoom. Let's see if make that work. You speak now. I muted you, so I can't hear you. If you're asking, I couldn't hear you.
We've heard someone before.
Yeah, that's true. So it might be. I don't think it's with Zoom.
We can try this one.
Good. Like that. I think we could try if you have the question to direct to Daniel later on by email. Do you think you could put your email on?
Yeah.
If you put it on there, then
Yeah.
they can ask the question as well. I don't think somehow we could, unfortunately, not hear. All right. Well, nevertheless, thank you everyone, both we're still here and on Zoom for attending. I know a bit of a technical hiccup in the beginning. Thank you very much for bearing with us. Thank you very much to Daniel for an excellent talk. For those of us here, we can move ourselves back to Chandler House for some post-talk refreshments. But otherwise, we will be back maybe not next week, but the week after for more speech science from talks. So do keep up with the updates from every possible source, and then you will hear something. But yes, thanks very much. This is the day.